Okay, I guess we can start.
All right, it is 2 minutes past 3 o'clock. And with that, I'd like to welcome everybody to this webinar with the title, Are the Investments in High-Resolution CRiceS Modeling Paying Off? My name is Morven Malwijk. I'm the moderator today, and I'm a researcher at the Norwegian Polar Institute. And I'm currently working within the CRiceS project, who is behind the organization of today's webinar. So before we dive into the topic of today, I'll give a little bit of a brief introduction of today's agenda. And for all your information, this meeting will be recorded, and that's good to keep in mind for the question session later on. I'll do a brief introduction of the topic and what we'll be discussing today, and then we start off with the main act of the day, which is a presentation by Julia Selivanova from the CMCC in Bologna, Italy, about the limited benefits of increased spatial resolution in CRiceS high-resolution climate simulations. After this 25-minute presentation, we'll open up for a panel discussion where Julia will be present, and we also have Dorotea Iovino from the CMCC, Marcello Vici from the University of Cape Town, and Francois Mazonet from UCL in Paris. And during this discussion, there will be an opportunity for the audience to ask questions. So if you have any questions to the panel, please write them in the chat and we'll forward them. I'll be monitoring this, and we'll also open up the floor afterwards, and we can unmute you or give you ability to talk and ask questions directly. So first of all, for those of you who don't know the CRiceS project, this is an EU Horizon 2020 project, and CRiceS stands for the Climate Relevant Interactions and Feedbacks. So the key role of sea ice and snow in the polar and global climate system. Now on the slide here, you can see the three main objectives of this project, and the overarching aim of our project is to improve the understanding of the coupled climate system in polar regions. And this is obviously done by providing new knowledge about both the ice, atmosphere, and ocean components of this system, and thereby also enhance the ability to respond to changes in these regions. The project is divided into multiple work packages with both observational and modeling objectives, and today's topic feeds into multiple of these work packages where we'll be discussing model shortcomings, discuss how sea ice processes can be improved in models, and how this then can finally lead to improved projections of future polar climates. So today's topic will be based on two recent publications by Julia from the CMCC about sea ice modeling. And the big question is, of course, why is this important? And that is because accurate modeling of the sea ice cover in both Arctic and Antarctic remains a major challenge. You can see an example figure here from just one of many publications, but according to recent assessments, coupled climate models, such as those participating in CMIP6, still struggle to accurately represent so simulate and reproduce variability, spatial patterns, and also underestimate recent trends in comparison to observations. And of course, the big question here is, why is this the case? And the scientific community points to many potential reasons, which we'll be discussing today. We have many critical processes in models that might be oversimplified, parameterizations that might be simplified, complex phenomena in the sea ice, like fracturing, ridging, rafting. We have wave interactions in the marginal ice zone, snow loading, melt ponds, drag on the ocean and atmosphere. All these processes are difficult to capture and simulate accurately. Another issue which many have been discussing recently at these models and many of the parameterizations that we use today were based on a sea ice regime that was thick and may no longer reflect today's changing climate. So as a result, some processes that were once considered negligible, such as maybe snow loading or melt bombs, have now become significantly more important and influential. However, in addition to these general model shortcomings, there's always been the issue of spatial resolution, which in climate models is very coarse. And many have argued that higher resolution is needed and believe that this may help to improve the models. So as we will learn today, the relationship between resolution and accuracy might not be as so straightforward as it seems. And I'm therefore honored to introduce Julia Selivanova, who will now present her findings and shed some light on this crucial topic. So with that, Julia, the virtual floor is yours.
Okay. Good afternoon, everyone. Thanks, Morwen, for the nice introduction. Now I share my screen. And one moment. Okay, this one. Okay. Okay. Do you hear? Do you see my screen?
Yes, very well.
Okay. Okay, great. Okay. Good afternoon, everyone. My name is Julia. I'm a postdoc at CMCC. And currently I'm working in a group of ocean reanalysis production. And my background in sea ice variability and representation in different ocean reanalysis and climate models. Today I will speak about limited benefits of increased resolution for sea ice in high resolution climate simulations. This work is based on my PhD project and two recently published papers. And I will take a moment to acknowledge Doroteo Jovino and Marcello Vicchi, who supervised me during my PhD. Why sea ice matters? Sea ice is a critical component of climate system which controls exchanges of heat, moisture, and gas between ocean atmosphere. It affects surface albedo. It involved in multiple climate feedbacks and represents a large unique ecosystem. The extent to which sea ice influences the climate system depends on its properties. Even though it forms only in high latitudes, its profound effects are not limited to regional climate, but spread further. Despite the two places being located in high latitudes, there are fundamental differences in the sea ice characteristics and variability. The contrasting nature of sea ice in two polar regions determine its different response to climate change. While the Arctic experiences very fast sea ice decline, the Antarctic shows modest expansion with large variability, which interrupted by rapid sea ice loss in 2017 and new record lows in recent years, which might mean regime shift or temporal multi-year variability. Given the role of sea ice in climate system, its proper representation is essential for climate modeling. CMIP6 climate models show high intermodal spread in simulating seasonal cycle and interannual variability. And they also struggle to capture overall expansion in the Antarctica region. One of the ways to enhance the representation of processes in high latitudes is to increase horizontal resolution. Better resolved oceanic and atmospheric mesoscale features facilitate the realism of large-scale climate in the model simulations. Different aspects of polar climate benefited from higher resolution, from AD-permitting resolution. So the question is, does the increased horizontal resolution, AD-permitting, improve the representation of sea ice in coupled climate models? So we start from the Arctic, and I will outlook the main results of the paper. Okay, in this study, we use the models participating in CRiceS MIP project. There are 6 models and 14 configurations with varying ocean atmosphere resolution. The ocean resolution varies from 1 degree to 1/4 degree, and the atmosphere resolution changes from 250 to 50-25 kilometers. We analyze historical and future runs. Okay, this slide shows Arctic sea ice over historical period. On the left, we can see seasonal cycle in sea ice area and sea ice volume. Black lines indicate reference data sets, satellite data for sea ice area, and ocean reanalysis PO mass for sea ice volume. And different colors represent different models, and different styles, line styles show their configurations. The models generally can properly capture annual maximum and minimum for both variables. For sea ice area, the spread is larger in winter if we exclude the outlier, while for sea ice volume, the spread is similar throughout the year. For sea ice area, we find the improvement with finer resolution, which is a result of resolved ocean currents in the Northern Atlantic and a more realistic ocean heat transport. The models generally overestimate sea ice volume compared to PO mass, since they struggle to simulate sea ice thickness. On the right, we can see a special pattern of March sea ice thickness, the months of maximum sea ice extent in the Arctic. With red and blue circles, I show increase in ocean and atmosphere resolution. We find no clear effect of resolution on sea ice thickness pattern, and nearly half of the ensemble shows no differences between the configurations. So sea ice thickness representation depends on the model used. The next slide shows interannual variability and trends over historical period. All models are able to reproduce overall sea ice shrinking, but with varying intensities. Most models underestimate sea ice trends compared to satellite data sets, which are shown by black symbols. Generally, there are less negative trends with finer ocean resolution. For sea ice volume, there are no straightforward impact of resolution on linear trends, because the effect of resolution on sea ice area and sea ice thickness differs between the models. Okay, considering that sea ice in the Arctic continues to melt, the question arises, when will the Arctic see its first ice-free summer? CMIP6 models predict the event to happen between 2044 and 2067. Okay, what if we can improve the prediction, selecting best performing models? To do so, we apply criteria combining mean state and linear trends. So we look at how close the models to reference product in simulation of September mean state and trends in sea ice area on the left and sea ice volume on the right. So different colors, again, indicate different models, and different symbols show their different configurations. We pick up models which are within 75th percentile and that fall into the left bottom part of the graph. At the end, we have 4 best performing models, one of which has coarse ocean resolution, others have eddy permitting resolution, and atmosphere resolution varies from 50 kilometers to 100 kilometers. In this slide, I show sea ice volume evolution from 1950 to 2050 in the Arctic and subregions of the Arctic. we analyze how fast the regions become ice-free. For the subregions, the threshold refers to 25% of average sea ice area during the historical period. Vertical lines indicate timing of first ice-free summer, black for satellite data, green for multimodal mean without model selection, and yellow with model selection. We see that model selection leads to closer agreement to satellite data in the regions where it already happened. We also find that model selection advance the timing of the first ice-free summer in the total Arctic up to 2047. And along with overall sea ice decrease, Arctic sea ice decrease, there are changes in the structure of sea ice cover. So the fraction of the marginal zone is growing, and by the middle of this century, it grows up to 50–80%, according to CRiceS MIP models, which suggest the shift of Arctic sea ice to the region similar to the Antarctica. Okay, now we move to the southern hemisphere. In this study, we use same models, adding AVI model and CHESS model. There are 8 models and 18 configurations in total. And to evaluate the role of horizontal resolution, we divide the models into 3 groups. Low resolution is the ensemble mean of low resolution ocean configurations. High resolution, the ensemble mean of high resolution ocean versions of the same models. And high resolution all is the same as previous, but including SIMCC and MPI models, which have only eddy permitting configurations. For the Antarctica, we analyzed only historical runs. Okay, this slide shows the mean state of sea ice cover over historical period. Again, we show here seasonal cycle in sea ice area and sea ice volume. Black line indicates the reference product. Individual low resolution models shown by light blue color, and high resolution by dotted lilac lines. Different resolution groups are shown by blue lines with different styles. The models generally are in good agreement with satellite data on capturing annual minima and maxima in for sea ice area. We find that increased ocean resolution in Antarctica leads to lower sea ice area, and low resolution group, which is shown by solid line, is in better agreement with satellite data compared to high resolution groups. For sea ice volume, we use 3 different reference products. There are 2 ocean reanalyses, GeoMass and GREP, and 1 satellite product calculated from NVSAT sea ice thickness. So 2 ocean reanalyses have similar seasonal cycle, but they have different variability from nearly April to December, while NVSAT sea ice volume has completely different seasonal cycle with earlier peak in August and larger values. Given that all reference products have different seasonality and there are no consistent and reliable data sets in the southern hemisphere, we analyze, we treat the results for sea ice volume with caution. So most models show very slow sea ice growth with maxima in October. The increase in ocean resolution leads to lower sea ice volume, especially it's seen in winter, while in summer it's less affected. Okay, the next slide. In the next slide, we analyze the spatial pattern, the effect of resolution on the spatial distribution of CRiceS concentration and CRiceS thickness. The maps show the average difference in CRiceS concentration between resolution groups and CDR on the left, and the difference in CRiceS thickness between resolution groups and geomass on the right. Low resolution ensemble shows lower biases compared to high resolution groups in September. And high resolution ensembles show larger negative biases in Atlantic and Indian Ocean sectors. In February, the differences are less noticeable between different groups, but high resolution groups slightly have larger negative bias in the Weddell Sea. For CRiceS thickness, we notice the little impact of the increased resolution on CRiceS thickness spatial pattern. Okay, this slide shows interannular availability and trends. We see that models do not capture the overall expansion over this period, and only one model capture positive trend, positive annual trend for CRiceS area and for CRiceS volume, but still it's very weak and lower than shown by reference products. We also analyzed linear trends over extended period. Starting from 1950, and there are more models showing positive trends. It happened due to reduced sea ice cover at the beginning of the run. Okay, our results show that the enhanced resolution of the ocean grid generally leads to less negative trends, but again, it's more strong for extended period. Okay, and as we did for the Arctic region, we analyzed, we assessed the historical performance of the models by combining mean state and linear trends. But for the Antarctica, we analyzed only CRiceS area. So we did it for February on the left, for September on the right. Ensemble groups, low-high resolutions shown by blue symbols. And we found that low resolution has lower biases in the mean, for the mean state for both months, and slightly higher biases for linear trends. Okay, to conclude, we find that coupled climate models can properly reproduce historical seasonal variability for both variables, for area and volume, but the intermodal spread is still large, especially for the Antarctica. All models can reproduce overall sea ice loss in the Arctic, but they fail to reproduce expansion in the Antarctica. We find no systematic relationship between resolution and sea ice representation, and the impact depends mainly on the model. So given the high computational cost of high resolution simulations, we think that the focus might be on improvement of sea ice model physics and parameterizations. And our study also confirms the need to distinguish marginal ice zone and to focus on this sea ice area. And given that marginal ice zone will dominate the Arctic sea ice cover in the near future, the model physics might require changes and adaptation to new region. Okay, I finish here. Thanks a lot for attention, and I stop sharing. Okay.
All right. Thank you very much, Julia, for that very nice and interesting presentation. This will give a very good basis for discussion, which we're going to start now. And this is hopefully a very interactive discussion. I'm sure there's many questions from the audience. So first of all, I'd like to introduce the rest of the panel that will be discussing with us today. And the way we're going to do this is I'm just going to introduce the topic. I have an introductory question that I'd like to ask all of you, starting with Julia, and then we'll open up also for questions from the audience. So if you have anything, burning questions to Julia or to any of the other panelists, please write them into the chat. I'll be monitoring that and we'll bring it up. So with us here today, we have Dorothea Iovina, also from the CMCC, who also worked on this project. Welcome. We have Marcello Vici from University of Cape Town, far south, and then we have Francois Mazenet joining us from Paris. So welcome and thank you all for coming. You're all experts on the field and eager to discuss. So in many ways, I think this is a very interesting study, but also a little bit depressing, maybe. Hoping that, you know, increasing resolution would be one of the solutions. And we'd, of course, hope to see some improvements from previous climate model versions. But it appears that there's not a lot of improvements. So Julia, based on your findings now, I guess the big question is, how do we move forward? So our findings, your findings indicate that increased resolution is not necessarily a simple solution just to improving our sea ice model simulations and predictability of the sea ice cover. So what other options do we have and what should we be focusing on forward?
Okay, so yes, increased resolution is not always the answer. There are other options, there are factors impacting the realism of sea ice. And first of all, it's inadequate model physics. So if we use the same model in using enhanced resolution, it doesn't mean that we will have improvement. It also can lead to less reasonable sea ice representation. So first of all, we need more realistic treatment of sea ice dynamics, thermodynamics, and interaction of sea ice with the ocean, atmosphere, and snow. So also sea ice thickness, which is still less accurate than sea ice concentration, and from its mean state depends the projection of sea ice in the future. And from the other hand, we don't have enough observations of sea ice thickness, so we can't constrain it in the models. So I think other points can be some persistent biases in the models, like clouds and radiation and winds, which also might which also might not be responsive to enhanced resolution. Yes. Yeah.
So there's lots of work to be done there, I assume. I'd like to give the word to Francois. Welcome, and thank you very much for joining us. You haven't been part of these studies at all, so it's really interesting to get an outsider's perspective on this. So what are your thoughts?
Sure. Thanks for the invitation. I'm really happy to join the discussion and the panel. Congratulations to Julia also for these two wonderful studies. I think they they really shed light on a question that we have been asking ourselves since a couple of years now about the role of resolution. I would like to temper a bit maybe the statement that resolution is unimportant, because that's a very quick way to summarize the findings. Well, first, because I want to frame the reality that resolution is maybe a loose concept in a way. Of course, we are talking here about changes often from 1 degree to a quarter degree of resolution, spatial resolution, and that's in the end a very tiny difference when you consider that the full spectrum of resolution available in current models goes from sometimes 4 to 5 degrees for intermediate models of intermediate complexity, all the way down to sometimes 1/60th of degree for regional configuration. And so it would be interesting maybe to ask the same question again, if we could make a more brutal sensitivity experiment comparing extremely coarse model to extremely high resolution model. So that's a first point. The second point that I think we have to keep in mind is the question of tuning. Obviously, the models that are run at higher resolution needed more resources to be run, and so as a consequence, less time could be invested for tuning those models, obviously. And so they have not received probably the same amount of attention or the same amount of care when it came to tuning. Probably only 1 or 2 simulations could be done with those models, meaning that they had, it's a bit of an unfair comparison in the end, because we are comparing models that have been extremely well tuned to new models that have received less tuning. And to conclude, maybe a third point, which I think is important, is also the question of the verification or the metric that we are using to make such claims. I think, if I understood correctly, that Julia, you have looked at large-scale CRiceS diagnostics, which I think are perfectly fine for assessing the climatic state in those models, concentration, thickness, CRiceS extent, CRiceS volume, etc. Now, if we were to look at the smaller scales, at the process level, it would be interesting to ask the question again. For example, if we think in terms of deformation rates of the CRiceS, highly localized dynamics of the CRiceS, velocity fields, maybe even mass balance terms, maybe we could start to see differences among the models because of processes that are resolved at the higher scales. So that's to say that I mean, the results are really interesting in the sense that from a larger scale perspective, we don't see much of an improvement, which, as you say, is probably a bit disappointing in a way, although many probably didn't expect something else, also because the forcing is so important. But I think these 2 studies really open up a lot of alternative questions that we could look at to confirm the findings.
Thank you very much. Francois, Dorothea, do you have any initial thoughts on that? And maybe particularly also towards Francois's comment there that, maybe it's a bit of an unfair comparison, or that we're just not fully developed yet.
Yeah, thanks for the word. Hello, everyone. I think that the work that Julia made during her PhD, it's strongly relating to the CMIP-like simulation and the metric that we applied to that. So I totally agree with Francois that actually running its eddy permitting resolution needs to a different probably diagnostic package, and we have to look at those data in a different way. But in the framework of CMIP, and it's where actually this resolution, this exercise was performed, we try to make exactly the same conclusion. So what we want to learn from this kind of numerical exercise, and then I have to agree with Julia that we don't learn much more than the standard resolution. But then following what Francois said, that of course, if you change the perspective of the study, and if you look at different processes into CRiceS, if you look at the dynamics more than the growth and the melts, of course, there are differences. we have started to do that with Julia during her PhD, and I also have to say that resolution also is not always a benefit for those processes, but the difference that we have are much larger. So the impact that we see when increasing resolution on the ensemble of different models is much larger if we go into the details of the processes. And also want to say that into the iris MIP exercise, the focus was, the focus on increasing the resolution was not on CRiceS itself, but we played mainly with the ocean atmosphere and see how resolution impact on those two main components of the system. And we have many papers from the Malcolm Roberts, that was one of the leader of this program, saying that the resolution in the atmosphere has large benefit on particular processes. If you look at the ocean, when you go to eddy permitting resolution, as also Julia mentioned, the North Atlantic drift is much better resolved. The heat transport into the Arctic is well reproduced. So I won't say the resolution doesn't matter. Resolution is not really the key solution for CRiceS models. And that's mainly because we are kind of oversimplify the mechanisms, both thermodynamics and dynamics. So for sure, we need to improve effort to add new parameterization, but also to improve the physics that we are solving into the process. What actually Julia highlight in her studies that if you stay on the Arctic, for example, she didn't show many details today on that, but she actually made a really nice analysis on the how the marginalized zone is reproduced in those models. And actually what is really impressive is that is totally wrong if you compare with observation. So it's totally wrong means that really any model into the Arctic can depict the transition that we're going through. So that means they're really missing a piece of the story here. So even though if you look at the total CRiceS and everything seems to be anyway similar or mimicking what we are expecting, if we go to ice type or to single process, then the situation can be worse. But that's not because of the model, just because the physics is not there. So the effort has to be to improve what we were resolving, improve observation, improve constraints. As Francois said, the tuning is also an issue. So for the high resolution MIP, there was no calibration at all. We just took actually what was done for the standard resolution, and we applied to the highest, to the middle, to the medium, or to the high resolution. So calibration and tuning was kind of missing here. So there are so many different aspects, but it was a huge exercise. So the main point has to be that if you want to run this kind of numerical runs, you spend a lot of money, computational cost, and time for doing that. We need to be kind of clever in set up all the program.
Thank you very much, Dorothea. I'd like to give the word to Marcelo and ask you, of course, the same things. What is the way forward? Where should we be focusing? And maybe one specific addition to that, well, we've been mentioning that physics need to be improved. And one of the main, but this is, of course, very broad. Is it your opinion, is it the thermodynamical processes? Is it more of the dynamical? Is it the balance? And why is it so that CRiceS volume, it's really thickness that appears to be the biggest issue here, much more than the concentration or the areal extent? Why is this so, and how can we move forward from that?
Thank you, Morven, and thanks to Julia for the great presentation, and good afternoon, everyone. My point is actually quite simple. I had very little expectation that high resolution was going to do something for two reasons. Because if it was going to do that, was through the improvement in the atmosphere and in the ocean. Because they are fluid, treated through basic principles, through basic laws. So in that particular case, increasing the resolution is bringing in the nonlinearity that are part of our inherent understanding of them through the Navier-Stokes equation. We treat CRiceS through a viscous approximation. So there's no reason why we should expect an increase in resolution is effectively doing something, because we are not adding any better physics in there. And the physics we have included in models is currently coming from a combination of one-dimensional vertical thermodynamic processes, which kind of combine from the Semptner model many years ago. They are just been expanding a bit more on these initial ideas that were built for larger scale climate considerations. So now we're asking those parameterizations that have been designed for large-scale seasonal balances to work and operate and elicit some sort of unknown behavior that is not in the equation, simply. So we are not treating CRiceS as a mechanical system, as something that's got its own properties, not to speak about the biogeochemical properties that are in the CRiceS that would make it even more complicated. And we just assume that by combining these vertical processes with its own timescales, with horizontal approximation, viscoplastic, elastic, trying to do our best into that one, which are all parameterization, they would respond to an increase in scale. That is pretty much a simple answer. While, I mean, we could have, there was no need to do it, but of course we're doing it because we want to improve the ocean and the atmosphere. And our secret hope was that these increased fluxes were going to somehow massage and help the sea ice to behave better. Unfortunately, this is not happening. Where to go? That is complicated. I feel like at these scales, I mean, it does make very much sense that we operate through essential climate variables, because those are the ones we can measure. If we try to measure sea ice concentrations, sea ice thickness with cores or individual points, we know that there's a lot of natural variability that we don't understand. Drift is also difficult to be measured from space, and we do major approximation because we basically measure drift through changes in concentration. So it's quite complicated unless we got the billions of drifters everywhere. So we can only improve the physical parameterizations of what we know, which means there's a long way now that we have exhausted and finished our options, and just hoping that the increase in resolution was going to help. A bit provocative.
No, but I think that's a good point. As an oceanographer myself, I'm very well aware that the biases in the ocean and atmosphere are very large, and this is, you know, maybe that's also maybe good to know that for the sea ice, the biggest problem appears to be the other parts, the other components, and not necessarily the sea ice itself. But if we focus on the sea ice models itself, are there any and maybe now I'm particularly looking at Francois, like what is your idea of what are the big issues? And like what are the problems that we are currently facing, not resolution related? And is like what is the way forward? And is there any progress?
Sure. I mean, the answer to such questions is always application dependent, I would say. But so if we are talking about climate timescales, which is probably the topic of today, I mean, you want to make sure first that ice has the surface covered by ice has the right albedo, right? Especially at the critical seasons. So surface processes like the formation of meltponds, the cycle of snow to liquid water conversion, etc., is definitely a critical one. And now a couple of models start to have meltpond processes, but it's not still automatic. So that's clearly one avenue of research. Then we have everything that concerns the marginal ice zone, as it was said by Dorothea. The really fragmentation of ice in from the continuum of the ice pack all the way down to the ocean is critical, and there are systematic biases in the width of the marginal ice zone in climate models, and this is a really tricky area because you really want to move from a continuum approach to an approach where you can even model individual ice flows and their interactions in that zone, interactions with the eddies of the ocean. So that's another key area of research. And then to name maybe a third one, I think I mean, that's maybe more for practical applications, but the land-fast ice distribution is also key, especially I mean in the Arctic, but also in the Antarctic, where we observe land-fast ice to anchor or to agglomerate around grounded icebergs, and then you can find polynyas downstream the land-fast ice. So I'm mentioning land-fast ice here because it's present in both hemispheres in different for different reasons, but also because it's a central piece in the polynya formation and in also in the dense water formation that can have very long-term climatic impacts. So I would say, yeah, these three would definitely be on the top of my list. And of course, rheology has been mentioned, but it was so obvious that I didn't want to mention it again.
Thank you very much. It's a long list and obviously a lot of work. And maybe Dorothea, I see there's a question in the chat that I'd like to ask you, and that also maybe feeds into my next question. You know, first of all, Letizia is asking in the chat that what we call high resolution, you know, in terms of sea ice, is maybe not very high resolution, and is that was also mentioned by Francois. So is just going even further, is that maybe another step? And how does this work then also feed into CMIP 7? Is there any idea of continuing with higher resolutions, or are there any other model improvements that we can expect or look forward to in the next generation of sea ice models in CMIP 7?
Yeah, I mean, to directly answer to Letizia question, actually, as Francois said, the resolution that we're using now, it's not enough if we want to resolve properly sea ice variability for the different process that we are missing. But then the point for the CMIP 7 is that there are proposition, and now we are kind of also kind of well-based to increase the resolution for the next exercise, having the 1/4 degree as default. At least that's what many centers is thinking to do. And then I don't know practically how many of us will be able to. But I think that the main point, I mean, since we know that sea ice itself is not largely impacted in a good way from resolution, I think the main point will be, as Francois says, to add these extra processes, they act at a smaller scale, they are still missing. So there's been big effort into at least the European community, but also for the US one or the Australian one, to add melt pond, to a new parameterization for sea ice, salinity, also to improve the interaction between the ocean and sea ice, to try to correct the melting and the growing and the drags between ocean and ice. I bet the same is doing the atmospheric community. So I think that, I mean, at least for this discussion and the US results, I think that this is the way to go. And I really hope that many of the improvements that we will have, hopefully, into the CMIP 7 for sea ice will come from the model, sea ice model itself, and not because of the interaction with the others. So the other component do better, so the impact on sea ice is somehow better reproduced.
Thank you. I'm curious, maybe this is not clear to a non-sea ice model, and maybe Julia, you can help me out. And so is there a big difference between the sea ice or the models that are used for regional prediction and operational forecasting of sea ice versus those that are used in the climate models that you studied? Is there a big difference, and is there maybe is it feasible to use those or such models in climate models in the future?
I think I'm not an expert in this question.
No, Marcello, do you have any insight on that?
Yeah, well, surely Francois can he's the expert in predictability and predictions in here, so he can come back after this one. But yeah, actually, your point is quite relevant here. I believe in terms of what I was talking earlier, the basic underlying equation, there are not major differences. But what Francois said is that now we're starting to resolve flow interaction. We are starting to look at individual flows movement. Like there are models used for prediction, for regional predictions, that they have flow size, thickness distributions, and they are also coming into global CRiceS, global ocean CRiceS models. People are just starting now to do the coupling with full climate models. So this is something mostly the Australians are doing it, and the Americans are working on this one by including the work done on individual flows and all the size distribution. I feel like these are interesting and probably promising subgrid scale parameterization. They will probably allow us to get a better understanding of the heterogeneity of sea ice, which may then play along with increasing resolution in the underlying ocean and atmosphere. I'm not completely sure that we have mastered the interactions, the local interactions. So it will always come down to a 1D and to probably the 2D, the viscoplastic assumptions, while dealing with the horizontal, with multiple flows, could be improved. I feel like we will have a better description of strains and stresses, and some rheology will get better, certainly at the scales of climate importance. That is true. I'm not completely sure that it will resolve the marginalized zone and the landfast. This is where I feel like we probably need to start measuring seriously, not just one single point, but having the opportunity, particularly the landfast, to re-establish longer-term stations that allow us, that can be reached from Antarctic bases or in the Arctic as well, which is easier and possibly can work better, to continue collect this data longer term to ensure that we can improve our parameterization.
Thank you very much. Francois, you have maybe some comments. I'd also like to remind the audience, if you have any questions, now is the time to pull them up into the chat for the panels, since we're getting close to the hour. But Francois.
Yes, I wanted to react on this question about prediction, because I think it's a good one, and it illustrates again that one conclusion might not be valid for climatic context as well as for other contexts. And if we think in terms of prediction, I'm not aware of any studies who looked at the role of resolution for the CS prediction per se. But if you are a user of the data, obviously you will prefer to have data distributed from a model that was run at a 12th of a degree or a quarter of a degree compared to data that was produced by a data at 1 degree or 2 degree, just because the ice edge location will be much more rich, have patterns, have information that you can really actionably use for your navigation. In terms of coastal processes as well, resolution could be an added value. Even if we are talking about no casting, like just prediction for the next couple of days, having data models that are used with data assimilation systems at high resolution have an incredible advantage over lower resolution systems. So that's also why I think efforts should be continued in investing those higher resolution configurations, is because they have value for people who are using it for very practical operational purposes.
Thank you very much. I see that there's a question to you, Julia, in the chat from Carolina Holmes at the British Antarctic Survey, asking if you have a hypothesis for why the Antarctic sea ice concentration was so degraded in the Atlantic Indian sector, specifically in the high-res simulations.
Okay, yes. So the high-res groups show the large negative bias in these regions. Yeah, probably because of warm bias in this region in high resolution configurations, I guess. I didn't check it, but it's just I guess.
If I can add a comment on Julia's one, I mean, Julia is now working on this simulation now. She changed a bit the topic, but we are going on with analysis, and actually what we saw is that the impact of the atmosphere and the ocean there, it's really large. So if you move the ACC location, you move the position of the jet, CI strongly reacts to that. So how you actually extend how you grow in thickness CIs, it's mainly relating to the interplay with the other two components in those locations.
Thank you very much. We're getting close, so I have one more question to the general panel, and feel free to speak out who has the strongest opinion maybe, but as an observationalist going out in the field, there's a big challenge, of course, you know, what are the big knowledge gaps, and particularly now all of you working with or within the modeling communities. Marcello mentioned that there's requirement for more data. Of course, we need various data to validate. This is a problem, particularly when it comes to sea ice thickness. Satellite products are luckily improving, but are there any specific aspects that require dedicated observational studies or process understanding that, you know, for a certain process that is very poorly constrained? Or what is your big shout to the observational communities on what is the need?
I can start replying to that. First of all, because for CIs, we have really few variables that are observed. So the only constraint that we have are mainly on sea ice concentration, has somehow recently on sea ice thickness. There are some observation on sea ice drift, but there are many other things that actually we would like to have. So even when Francois mentioned the short-term forecast or the seasonal forecast, even for those one, we have no enough constraint from observed data set. So, and another point that we have in polar region that is really important is uncertainties. So we have really large uncertainties. So even on sea ice thickness data sets, they make them really hard to be used. So if you want to have data simulation, if you want to have calibration of sea ice model based on that, it's I mean, you really need to know the quality of your observation, and we know that's still poor. Even for the new products that we have. So I think that's a quantification of uncertainties, probably having an ensemble of observation for key variables, or new methodology actually to work on algorithms like machine learning could be one way, or hybrid modeling could be another way. I think that there is a lot to do, trying to combine as much as we can the classical physical model with the new observation.
I can continue. I would pick one very precise example to answer your question, Marvin, and I would like to go to the Southern Hemisphere, where we know at the moment the situation is really alarming, in the sense that we have observed these negative anomalies. I think that was shown on one of the slides from Julia. The thing is that at the moment, the recovery of ice from summer to winter is extremely slow, and this has happened for 2 seasons in a row, where really the seasonal development of the ice extent has been lagging behind and has tracked the climatology 2 or 3 or 4 standard deviation below the normal. So what I think it could be really urgent is to understand what is happening from the sea ice surface to maybe the bottom of the mixed layer in that context, Is there anomalous amounts of heat in the upper ocean that sort of delay the ice formation? Are there other processes that we are not capturing with models? So by focusing on a case study like that, I think we can learn a lot. So this would imply, of course, to go on the field almost immediately, because we are talking about the next growing season. But sometimes by focusing on extreme cases like those, you can understand a lot about the system.
Thank you very much, Francois. I think that's a good suggestion, and I understand there's a lot of work to be done, and there's lots to discuss. Unfortunately, we have reached the hour, and I think we could continue discussing this for many more hours. Unfortunately, we're out of time today, but I would like to thank you all for joining this panel. Thank you, Julia, for a very nice presentation, and congratulations on this paper. For the audience, if you're interested, the recording of today's webinar will be made available on the CRiceS website, EU Horizon 2020 CRiceS. And here you'll also find more updates about recent science coming out of this project, and other updates about the topic. So stay tuned for lots more exciting findings to come out, and I hope you all feel motivated and inspired to keep working on these big questions, knowing that we need to keep working on improving our models. Resolution is important, but not the only thing, and in these specific simulations, it doesn't seem to have led into big improvements, but a lot of work to be done there. So thank you, everyone, for joining today, and I wish you a nice continued afternoon and evening.
Thank you, everyone. Thank you, Morgan.
Thank you. Thanks.
Yep.